Namaste my dear students, welcome to online classes of Vivekananda PU College Puttur. Hope all of you are enjoying the online classes and making best use of it. In this video, I am going to start second chapter, that is electrostatic potential and capacitance. The word potential is familiar to us. In first PUC, we have studied the concept of potential energy in case of gravitational force field and in case of spring, in case of a spring. When an object is held at a height of h from the surface of earth, we say that it has some potential energy mg into h. If that object is shifted from that position to some other position, its potential energy changes. That means potential energy depends on its position. So potential energy is nothing but it is the energy possessed by an object by virtue of its position. Similarly, in case of a spring, when a spring is compressed or stretched from its original position, we say that it possesses certain amount of potential energy, and that potential energy is called elastic potential energy. Right. Now in previous chapter, that is electric charges and fields, we studied the concept of electrostatic force. We studied Coulomb's law. We obtained an expression for electrostatic force of attraction or repulsion between two static charges. So electrostatic force of attraction between two charges, it is given by 1 over 4 pi epsilon naught into Q1 Q2 divided by R square, electrostatic force. Instead of Q1 and Q2, if I consider source charge capital Q and some test charge small q, then force between the source charge and test charge is given by the expression 1 over 4 pi epsilon naught Q into Q divided by R square. In that chapter, we define one more term, that is electric field intensity. Electric field is given by force divided by magnitude of test charge, force divided by magnitude of test charge, which is equal to 1 over 4 pi epsilon naught into Q, that is source charge divided by R square. Here R represents distance from the source charge to the point where electric field intensity is measured. Now this quantity is called electric field intensity, and it is defined as, it is the force, electrostatic force per unit charge, electrostatic force per unit charge. Now this electrostatic force or electric field, it is conservative force. The important feature of conservative force is, in case of conservative force, amount of work done depends only on initial and final position. If you move an object from one point to another against conservative force, then amount of work done in that process is stored in the form of potential energy. We studied this concept in the case of gravitational potential energy. If you lift an object from ground, generally at the surface of earth, we take potential energy is equal to 0. If object is shifted to height h, its potential energy becomes mgh. Now what is that mgh? Mgh is the potential energy of that object. At the same time, it is the work done in shifting that object from ground to that particular point against the gravitational force. So work done is given as potential energy. Similarly, in case of a spring also, amount of work done in compressing a spring or stretching a spring is stored as potential energy, that is called elastic potential energy. Now this electrostatic force is also conservative in nature. That means in case of electrostatic force field, if external force, with the help of external force, if certain amount of work is done, that work done is stored as electric potential energy. In gravitational force field, gravitational potential energy; in case of a spring, elastic potential energy; and in case of electrostatic force field, potential energy is called electric potential energy or electrostatic potential energy. Now let us consider, or let us try to understand few terms with the help of a small example. Consider a point O somewhere here. Okay, point O. At this point O, I'll place a source charge of magnitude Q with positive polarity, a positive charge Q, let it be a source charge. Okay, next I'll consider two arbitrary points somewhere here, one point as point P and some other point as point R, arbitrary points. And one more point somewhere here, let us consider this point is at infinity, that is at infinite distance. Now we know that a charged particle produces electric field in its surrounding region. What do you mean by that, electric field? Electric field is nothing but it is the space around a charge or charged particle in which if another charge is placed, it experiences electrical force. Now this charge produces electric field in its surrounding region. In that electric field, if you place another charged particle or charge, that charge will experience electrostatic force or simply electric force. Right? Now, what is the range of that electric field? Up to what distance this electric field exists? That is, electric field exists up to infinity. At infinity, electric field or electrostatic force becomes zero, because we know that electrostatic force or electric field is inversely proportional to square of the distance, that is from Coulomb's law. F is inversely proportional to R square. When this R becomes infinity, then only electrostatic force or electric field reduces to zero. That means that electric field extends up to infinity. So starting from the charge, source charge, up to infinite distance, electric field exists. Now, at infinity, if you consider this point at infinite distance, the infinity point, at infinity, R is equal to 0. Okay, R is equal to 0. When R is equal to 0, force, electrostatic force or electric field, it is inversely proportional to R square. When R is infinity. When R is equal to infinity, magnitude of electrostatic force is 0, or in other words, if you consider the electric field, force per unit charge, electric field is also equal to 0 at infinity. Okay, at infinity, electric field as well as electrostatic force is equal to 0. If this is the case, no force here, no work done. If there is no work done, then potential energy is 0. So at infinity, electric potential, electrostatic potential or electric potential is equal to 0. Reason is at infinity, magnitude of electrostatic force reduces to 0. No force, no work done, that means no potential energy. Now consider a charge of magnitude plus Q, that is test charge. Test charge is at infinity. When this charge is at infinity, magnitude of force acting on this charge, I will consider it as F infinity, electrostatic force acting on plus Q. It is at infinity, therefore electrostatic force F is equal to 0. F infinity is equal to 0. Since electrostatic force is equal to 0 at infinity, at this point potential energy, we use the notation U for potential energy. So potential energy of small q at infinity is equal to 0. Potential energy possessed by that charge at infinity is equal to 0. Right. Now, if this charge is moved towards the source charge, distance reduces from infinity. When the distance is finite, electrostatic force comes into play. Now we considered a positive source charge as well as positive test charge. We know that force between like charges will be repulsive, so this charge will try to repel this charge towards infinity. So that means if you want to shift this test charge from infinity to a point near the source charge, certain amount of external force is necessary. So with the help of that external force, we can shift this test charge from infinity to point R or infinity to point P or to some other point. Okay, so external force is necessary. Now imagine This test charge is displaced from infinity to point R with the help of external force, F external. Now charge reaches this point, plus Q reaches point R. Now point R is at finite distance, the distance is not equal to infinity. So due to this charge, test charge at this point will experience electrostatic force. It will experience electrostatic force. If it experiences electrostatic force, under that condition, so here at in point R, electrostatic force is non-zero. If electrostatic force is non-zero, there will be potential energy. Now potential energy at R is also not equal to 0. It is also non-zero. Further, if you shift this charge from R to P, again external force is necessary. With the help of external force, if you shift the charge plus Q, test charge from R to P, when it reaches here, at this point, electrostatic force is non-zero. If it is electrostatic force is non-zero, then at this point potential energy is also not equal to 0. Right. Now we started from the point where electrostatic force is equal to 0, or potential energy, electric potential energy is equal to 0. We used an external force to shift this positive charge towards the source charge. So we pushed this test charge towards point R, then to point P. So with the help of external force, there is a force, there is certain amount of displacement, surely there will be certain amount of work done. Now let us try to write the expression for work done in different cases. Okay, work done in different cases. Now first of all, imagine or consider the case between infinity and point R. Amount of work done in moving that plus Q test charge from infinity to point R, I'll use this notation, W work done in moving that charge plus Q from infinity to point R is equal to, now we know that electrostatic force is conservative in nature. That means in case of electrostatic force field, amount of work done is stored in the form of potential energy. Here potential energy of plus Q is U infinity, or it is equal to 0. When it reaches here, its potential energy is UR. So therefore amount of work done, it is given as potential energy, so it is equal to change in potential energy, that is UR minus U infinity, final potential energy minus initial potential energy. But we know that U infinity is equal to 0. Therefore, this is equal to U infinity is 0. Therefore, it is equal to UR. Actually, we are calculating the potential energy difference. Potential energy difference. But one of the quantity is 0. Therefore, the amount of work done is equal to UR. Now, what is this UR? UR is nothing but it is the potential energy. UR is the potential energy of Q, because work is done on this. So potential energy of charge Q at point R. UR represents potential energy of Q at point R. Similarly, if you consider these 2 points, infinity and point P, amount of work done in shifting the charge from infinity to point P can be written as, now the final point is P and potential energy at that point is UP. So potential energy at P minus potential energy at the starting point, that is U infinity, but U infinity is equal to 0, therefore it is equal to UP. Now what is this quantity? What is this quantity? It is nothing but potential energy of charge Q when it is at point P. Potential energy of charge Q when it is at point P. Right? Next, let us consider these 2 points. These 2 points. Charge Q is shifted from R to P. In this process, what is the amount of work done by the external force? Amount of work done in shifting the charge from R to P is equal to final potential energy P at P, or potential energy UP minus initial potential energy R. Now we started from this point, final point is P, therefore UP minus UR. Now these two are the non-zero values. UP is not equal to 0, UR is also not equal to 0. Now this term is called potential energy difference. Potential energy difference between points P and R. Potential energy difference between 2 points. I think it is clear. At infinity, remember this point, at infinity, potential energy of a charged particle is 0. That is because electrostatic force is 0 at infinity, therefore potential energy is 0. So from this point, we shifted a charge with the help of external force and expression for work done in each case. Infinity to R, potential energy at infinity is 0, then this difference is equal to potential energy at R. Infinity to P, potential energy difference, one of the quantity is 0, therefore the difference represents potential energy of Q at point P. WRP, if charge is shifted from one point to another where potential energy is non-zero, under that condition the work done is equal to potential energy difference or change in potential energy, one and same. So potential energy difference. Okay, so now we reached this point by pushing the charge from Q from infinity to point P, we reached this point. At this point, if you remove that external force with the help of which the charge Q is shifted from infinity to P, if you remove that external force, then straight away this charged particle will be repelled by this source charge back to infinity. That means this charged particle will move like this. When it moves, its potential energy, that is UP, potential energy, gets converted into kinetic energy, and when it reaches here, potential energy completely reduces to 0. Same as an object held at height h from the surface of Earth. If you hold it like this, its potential energy is mgh. If you remove the force, object moves in downward direction, its potential energy gets converted into kinetic energy. When it reaches the ground, its potential energy reduces to 0. Okay, so now here this potential energy is called electrostatic potential energy, or simply electric potential energy. Electric potential energy, electric potential energy difference. That is the case of a charge Q. Now let us make small change here, or we will discuss one more condition here. In the previous chapter, using Coulomb's law, we derived an expression for electrostatic force between two charges, or due to a source charge Q, magnitude of force acting on a test charge small q, if the separation between them is equal to r, is given by F is equal to some 1 over 4 pi epsilon naught Q into Q divided by r square. Now it is electrostatic force. It represents electrostatic force. The same electrostatic force in case of unit positive charge, in case of unit positive charge, is called with different name, that is electric field, which is given by, electric field is given by 1 by 4 pi epsilon naught Q divided by r square. Electric field, it is force, this is also force, but one condition is there, it is in case of, or it is the force per unit charge. Same quantity, but when it is in case of unit charge, we use different term and different notation to represent that electrostatic force. In the same way, in case of potential energy also, for due to a source charge, potential energy of any random charge q, it is called electrostatic potential energy, and work done, it is stored in the form of electrostatic potential energy. Instead of q, if you consider unit positive charge, in case of q potential energy, if you consider unit positive charge plus 1 coulomb charge, under that condition potential energy of that unit positive charge is simply called potential, electric potential. Okay, so it is called electric potential. In case of any charge, potential energy, electrostatic potential energy. In case of unit positive charge, electrostatic potential. Now what is electrostatic potential? It is nothing but it is the potential energy possessed by the unit positive charge. Potential energy possessed by the unit positive charge. Now, and notation for, we use notation V. So electrostatic potential is represented using capital V. Notation for electrostatic potential is capital V. Now I'll make a small change here. Instead of considering positive charge plus q, I'll take unit positive charge here. Okay, unit positive charge. Unit positive charge at infinity. Source charge is same, that is plus q only. Now when unit positive charge is considered at infinity, electrostatic force experienced by this charge is now electric field. It is equal to 0 at infinity. We know the condition, distance is infinite, therefore electric field is equal to 0. If electrostatic force is equal to 0, potential energy of this unit positive charge is also equal to 0. So at this point, potential energy of unit positive charge is called potential, and we use notation V. So therefore potential at infinity is equal to 0. With the help of some external force, if this unit positive charge is shifted from infinity to point R, when it reaches here, electric field at R is non-zero. If electric field or electrostatic force on unit positive charge is non-zero, under that condition electric potential at this point is also not equal to 0. I'll take it as some V1, potential at R. Next, when it reaches point here, if unit positive charge is shifted from infinity to point P, here also electric potential is not equal to 0. Sorry, electric field is not equal to 0. So electric potential is also not equal to 0. I'll take potential at this point as V. V1 here, V here. Or to avoid confusion, let it be VR and VP only, similar to previous case. Okay. Now let us try to write these conditions in case of unit positive charge. I'll write here. If that unit positive charge is shifted from infinity to point R, then amount of work done in shifting unit positive charge, now it is in case of unit positive charge, amount of work done in shifting unit positive charge from infinity to point R is equal to, we know that work done is stored in the form of potential energy. So final potential energy of unit positive charge minus initial potential energy. Now VR minus V infinity, but V infinity is equal to 0, therefore this is equal to VR. Now what is this VR? What is this VR? VR is nothing but electric potential at point R, electric potential at point R, due to which charge electric potential is produced? Due to source charge. So due to Q. Similarly, if you consider the movement of charge, unit positive charge from infinity to point P, under that condition amount of work done from infinity to point P is equal to Vp minus V infinity, potential energy difference. V infinity is 0, therefore this is Vp now. Now what is Vp? What is Vp? It is electric potential at point P due to source charge Q. Because in the electric field of this source charge, we are shifting unit positive charge. So electric potential at P due to Q. Similarly, if you consider points R and P, amount of work done in shifting the charge from R to P, work done is equal to final potential energy of unit positive charge, that is electric potential at P minus electric potential at R. Now this term is called, this is potential at point R, this is potential at point P, because one of the term in the difference is 0, but here these two are non-zero values. Now it is called potential difference. It is called potential difference between the points R and P. Okay, potential difference between the points R and P. Same thing here, potential energy, because we considered charge of magnitude Q. Here we considered unit positive charge. In case of unit positive charge, potential energy is called electric potential V. So work done is equal to change in potential energy, same concept. So when one of the term is 0, the difference is equal to potential. Okay, it is the so these are the conditions. Now with the help of these points, let us try to define two terms. One is electric potential at a point, and another one is electric potential difference between 2 points. Electrostatic potential, or simply electric potential. Okay, let us try to define this term, important from the point of view of board exam. For 1 mark, define electric potential at a point. Now definition of this electrostatic potential is here in the mathematical form. Let us put in, or let us define it in sentence. Now electric potential or electrostatic potential at a point, it may be R, it may be P, electrostatic potential at a point due to we considered a source charge, now it is a point charge, due to a point charge. Okay, point charge is what is that electric potential? Electric potential is nothing but it is the work done. So it is the work done. Okay, is the work done, in which case it is the work done in case of unit positive charge. Therefore work done per unit charge. Okay, work done per unit charge, it is the important term, work done per unit charge. In what condition? In bringing that unit positive charge from where to where? Infinity to that point. Potential at point R, it is nothing but amount of work done in bringing unit positive charge from infinity to point R, isn't it? So work done per unit charge in bringing it from infinity, okay, bringing it from infinity to where? To that point at which electric potential is measured. If you measure potential here, work done in bringing charge from infinity to R. If you measure electric potential here, work done in bringing charge from infinity to point P. To that point, one more condition is there, against the electric field. See, electric field direction is like this because we considered positive charges here. We applied an external force in opposite direction. That means our external force is against the electrostatic force or electric field. So we can add that here, against the electric field. This is the definition of electrostatic potential or potential at a particular point. Define electric potential. This is the answer. Electrostatic potential at a point due to a point charge, that is source charge, is the work done per unit charge. Work done per unit charge in bringing that charge from, or bringing it from infinity to that point where electric potential is measured against the electric field. Okay, this is the definition of electrostatic potential. Next, we will define one more term, that is potential difference between 2 points. This is also important. Potential difference between 2 points. Definition of potential difference is here. What is this now? Now this term is nothing but it is the amount of work done in moving a unit positive charge from where to where? From one point to another. It is not from infinity. One point to another, again against the electric field. So potential difference between 2 points. Between 2 points is the amount of work done, again same condition, amount of work done in what process? In moving a unit positive charge, or simply unit charge, unit positive charge, amount of work done in moving a unit positive charge from one point to another. Okay, one point to another, again against the electric field. Now this is the definition of potential difference. Potential difference between 2 points is the amount of work done in moving a unit charge from one point to another against the electric field. If I consider some point S here, potential difference between these 2 points is nothing but amount of work done in unit positive charge, in moving unit positive charge from P to S, which is equal to potential at Vs S minus potential at P. Work done in moving unit positive charge from one point to another against the electric field is called potential difference. These are the two definitions important for 1 mark. Okay. Next. Now we defined electrostatic potential and potential difference. Now if you consider this electrostatic potential or electric potential, it is a scalar quantity because it is work done. We know that work done is a scalar quantity. So electrostatic potential is also a scalar quantity, which means it has only magnitude. And if you try to write the unit of this, if you want to get the unit of this electric potential, now electric potential is nothing but, or electrostatic potential is nothing but work done per unit charge. If W is the amount of work done in case of charge Q, then V is the work done in case of charge unit positive charge, that is 1 coulomb. If that is the case, if you relate these two quantities, it will be V is equal to W divided by Q. That is the definition. Work done per unit charge. Work done in case of charge Q divided by magnitude of charge. This equation is similar to electric field E is equal to F divided by Q. Force on charge Q divided by magnitude of charge gives force per unit charge. So work done per unit charge, W divided by Q. Now what is the unit of work done? Work done is measured in terms of joules, okay, divided by unit of charge is coulomb. So unit of electric potential is joule per coulomb, or equivalent unit is, or it is equal to, or equivalent unit is volt, and notation is capital V. Okay. So electrostatic potential or electric potential is expressed in terms of the unit called volt, and it is V. Now here 1 volt is equal to 1 joule per coulomb. Actually, it is the definition of unit of electric potential. If 1 joule of work is done in moving 1 coulomb charge, then potential is said to be 1 volt. So unit of the potential is a scalar quantity. Relation between electric potential and work done and magnitude of charge V is equal to W divided by Q, and the unit of electric potential, that is volt, and notation is capital V. Okay, so this is also important. Remember these things. Okay, I will stop here. In the next video, we will derive an expression for electrostatic potential at a particular point. One important derivation, so that we will discuss in next class. Thank you.